Okay, so we're going to look at basically how to convert between rectangular coordinates and polar coordinates. Rectangular coordinates, those are the ones you've looked at before, the x comma y. 5 comma 4 means right 5 and up 4. Polar coordinates uses your radius or the magnitude and your argument, basically. So things you've been working on, just looking at them in a slightly different way. So r is the magnitude, and theta will be the argument. So your first statement is just trying to get you to compare some things you've already looked at. If you have 2 points with rectangular form, you know that the x and y coordinates have to match up. And on this, instead of y2, it should be y1. So you're matching up. Point 1 has the coordinates x1, y1. Point 2 has the coordinates x2, y2. If the points are the same, then their x and y coordinates match. No big deal there. You've done that before. We're going to look at, does the same thing hold true for polar coordinates? So if we end up at the same location, and that's what this is saying, same location, do the radius or the magnitudes and the arguments have to be the same. So you're going to look at 2 directions. It's if and only if. Use the double arrows, it means you can read both of those. So if R1 equals R2 and the angles are the same, does that mean the points are in the same location? And if the points are in the same location, does that mean that the magnitudes and the angles are the same? So with your partner, take a couple minutes, figure out if what you think are both of those statements true, and if they're true, just fine. If they're not, come up with a counterexample. Okay, so the first statement, same radius, same angle, you end up at the same spot. Thumbs up, thumbs down. Yes? Okay, yes. So that one's pretty clear, definitely true all the time. Did you end up at the same spot? Did you have to have the same angle to get there? No. Think of your unit circle.
So it can be
So give me an example of an angle.
35 degrees.
35 degrees, okay. What's another angle that would end up at the same spot as 35 degrees?
It's called
Negative
145.
325.
Okay, negative, how did you get that?
And then I took just negative 360 plus that.
Right. We could add on multiples of 360 degrees to an angle and end up back at the same spot. Here, let's look at it. 35 degrees. Might be something like that. Well, negative 325. We'll be going around the other way. We end up at the same location, but a different angle to get there. What's the connection between 35 and 300? Negative 325. They're 360 apart, right? So if we modify the statement just a little bit, we can say P1, if the points are equal in polar form, if and only if, well, the radius has to be the same. They have to have the same distance from 0, 0. And theta 1 equals theta 2 plus 360 degrees n, where n is an integer, and that's accounting for the complete turns around the circle. radians in the same spot. If we were talking about radians instead of degrees, instead of 360 n, what would we have there? 2 pi, right, 2 pi n. So we could have theta 1 equals theta 2 plus 2 pi n if in radians. Okay, exact same concept, the idea you can turn around the circle, end up at the same place. So what we have next is we're going to start looking at how do we convert things from polar form to rectangular form, basically. How do we figure out what the x and y are? So we're given our magnitude of z is 2, and the argument of z is pi over 6. So what I like to do is just sketch it. First one, let's see, pi over 6, which quadrant is pi over 6 in? First one. Okay, so we know we're in quadrant 1, it's about 30 degrees. So I'm going to sketch vector. We know this angle is pi over 6. What's the length of that vector? 2. Okay, so we know the vector. Basically, we need to figure out our x and our y coordinates. So I can just draw it in. Here's y, here's our x, here's a right triangle. Yes, Alex?
Continue if you're gonna say
Nope,
something.
nope, go ahead, what's your question?
No, it's not a question, I was gonna solve.
Yes, good, great.
You could take the cosine pi over 6 in radians is equal to x over 2.
Excellent, yes, exactly. Just use your right triangle trig stuff. We work with radians just like we do degrees, cosine adjacent over hypotenuse. So 2 cosine pi over 6 is our x. What would we use for the y coordinate? What about the y coordinate now?
Sine.
Sine. So that's the idea. We're just using our trig stuff. Sine pi over 6 equals y over 2. 2 times the sine pi over 6 equals a y. Now, what did the 2 represent? The hypotenuse, right? Our magnitude. So the idea of this 2 was our magnitude. And the pi over 6, what was that? The angle, the arc. Okay. We could set up that trig function each time, or like on our unit circle, which one gives us our x coordinate? What trig function corresponds with the x coordinate on the unit circle? Cosine. Shortcut, we can just do 2 times cosine over angle, because that will give us our x coordinate. And then, or not 2 all the time, but our magnitude. So our magnitude times cosine of our angle always gives us x coordinate. Our magnitude times sine of our angle always gives us the y coordinate. Do you remember what's the cosine of pi over 6? No, not 1. 30 degrees cosine. Square root of 3 over 2. So we have 2 times square root of 3 over 2. So square root of 3. And then what was the sine of pi over 6? Not 1. 1/2. 2 times a half is 1. So our, in rectangular form, we would have square root of plus I. The great thing is we can use that pattern all each time. So convert 4 over to rectangular form. Okay, so again, we can make our triangle and do like we did before, where we know that our magnitude times cosine of our angle would give us the x coordinate. And then 4, and this is the magnitude, times sine of 135 would give us our y coordinate, well the y coordinate has an I with it. What do both of these have in them? What numbers in both 4 cosine 135 and 4 sine 135? 5. Oh, we could factor out of this. We could factor, right? We could factor out. So we could, let's see, let's simplify and then we'll come back. So cosine 135 is
2 over 2.
Where's, yep, negative square root of 2 over 2 plus 4 square root of 2 over 2 times our I. So we get, in this case, negative 2 root 2, which should be around 2.8, so they're negative 2.8, and then plus 2 root 2I. Here we could have factored out the 4, so we could have written this as 4 times cosine 135 degrees plus I sine 135 degrees. And the only reason I'm pointing that out to you is this would be called polar form. As you can see here, magnitude is written out in front, and then you have cosine of your argument plus I sine of your argument. Any questions so far? So then if we just gonna formalize a little bit, rectangular form again is your XY order comparison system you have. Polar form, you have R is basically the magnitude, which is that distance from 0, 0. And theta is the argument. Okay, or the number of degrees you have to turn counterclockwise. Also could be in radians. So the polar form looks like R, and then in parentheses cosine of your angle plus I sine of your angle, just like we had before on the last page. The shortcut way of looking at that, if we look at this, we have cosine, and then I, and then sine. So the abbreviation is cis. C for the cosine part, I for the imaginary part, S for the sine. And that's all that part is saying. So the last problem we're going to look at, we're going to write 3 minus 5i in polar form. What are the 2 things we need for polar form? Magnitude and argument. So with your partner, find the magnitude and argument for 3 minus 5i. Okay, so just walking around, magnitude, I don't think there's much from there. 3 squared plus 5 squared, and you get 34, so you have the square root of 34 is your magnitude. The argument, tangent of theta is 5/3, so theta was just a little bit more than 59 degrees. then our argument, okay, when I'm looking at working with right triangles, I just worry about the lengths, because then later we'll look at, okay, do I need to do 360 plus it, 360 minus it, or same thing with 180 if we're in quadrant 2 or 3. So we're 59 degrees short of being going completely around the circle, so our argument is 360 degrees minus 59 is 301 degrees. So then we write our answer, our polar form. Three minus 5i in polar form would be the square root of 34 times cosine of 301 degrees plus square root of 34 cosine, not cosine, sine of 301 degrees times our I.
Can the argument not be needed?
Argument, let's see, it could be, like he could have done this, the negative 59 degrees, and that's equivalent geometrically. Typically, you'll see the argument is between 0 and 360, but will be reduced or changed over to the equivalent angle. And you will also see this written, instead of writing square root of 34 times both of them, that will be factored out. So you'll see magnitude factored out, and cosine of 301 degrees plus I sine 301 degrees. And an even shorter way of writing it, for the cosine plus I sine part is cis. So you see the square root of 34 times cis 301 degrees. The nice thing is, if you're not sure if you converted it correctly, you could take that expression and multiply it out, so you can get 3 minus 5i. And it might be just a couple of decimals